Hello. In this presentation, I'm going to be discussing some of the introductory ideas in chemistry as it relates to matter. This is an important conversation because we have to talk about what matter is before we can talk about how different substances interact and things like that. And also, we're going to have a brief discussion on how matter is classified so that some of the vocab words that come up in chemistry will make a little bit more sense. So the first part of this discussion is trying to figure out what matter actually is. As a general principle, you can think of matter as something that has mass and occupies space. And so all of this stuff is made up of tiny little atoms. Many of you have heard of atoms before. We say there are about 100 unique types. And when we talk about these types, we mean the elements, which I'll talk about later on. So the elements are on the periodic table. Lots of them you're familiar with. Oxygen, carbon, nitrogen, hydrogen, helium, things like that. Those are all individual atoms of stuff, and those are called elements. And all matter is made up of these different elements. Some different things, just anything that you would think of, all right? So here we have a picture of water and trees, the earth itself. The sky, this is an interesting one. Lots of people think that air doesn't have anything in it, but really air is made up of nitrogen and oxygen mostly, and that does have mass. If you move your hand through the air, you can feel the particles moving around your hand, and it makes it feel like a sort of wind, and that is the matter that you're feeling. And so it does have mass, and it does take up space, and so the air is filled with matter as well. So something that doesn't have matter, well, you have to think it would either not have mass or not take up space. There's nothing in reality that has mass but doesn't take up space. However, the other one, you can think of perhaps something that has space but doesn't have any mass to it. And if you reflect on that for a minute, you might come up with empty space, like outer space, the vacuum of space, where there's nothing out there except for some very, very rarefied plasma particles in the intergalactic sort of space. And so it's pretty much empty. There's no mass in there. There's no matter, and so it's empty space. And that wouldn't be considered matter, but anything where there is matter. So everything on the Earth, everything on the Sun, that is all made of matter. Someone in class brought up antimatter as another example of something that's not matter. That's absolutely right. Antimatter is not matter. I'm not going to get into right now what antimatter is, but it's fundamentally a different sort of particle. It has a different sort of makeup than matter does, and it's sort of, in many ways, the antithesis of matter. And so space and antimatter, both of those are not matter as we're used to interacting. So one aspect of matter is the different states of matter. You're familiar with these probably, solid, liquid, and gas. Something that we're going to discuss in here is that solids have definite volume and shape. What that means is that they don't change. The volume and the shape stay the same. So that's what we mean by definite volume and shape. Liquids, on the other hand, they keep their same volume, so their volume doesn't change, but they can take on variable shape. If you dump a liquid from one container into another container, it's going to take on the shape of whatever the bottom of that container is. Gases, even more, they completely fill up whatever container they're in, not just like the bottom. They don't just fill up the bottom, they'll just spread out, and so their volume can change and their shape can change. And so that's something to think of and to consider when you're considering different states of matter or how matter is arranged. Solids, you can see, are really close together, and those are nice, organized, compact sort of particles. Liquids are more spread out, kind of more disorganized, and if you could see movement here, the liquid particles are moving a little bit faster. Gases are the most spread out and very disorganized in the way that they move. Looking here, you can see that there's also another fourth state of matter. This is called plasma. And so what happens with plasmas is that the particles get moving so fast that they end up leaving their electrons behind. When I think about this, I think sort of like in the cartoons when a character would run off and it would leave, it'd be moving so fast that it would leave its shoes behind or its hat or something like that. I think that's kind of like what happens with these plasmas. The particles are zipping around, moving around so fast that they just completely leave their electrons behind. And because they left the electrons behind, they become ionized, which means that they're charged particles. When you think about places where plasmas exist, something that you should think of on our sun is made mostly of plasma. Also on Earth, in a lightning bolt, it gets so hot that plasma is created. And some of you might have seen those little electric balls that look like they have sort of lightning bolts coming out of it, and you touch it with your hand, and the little lightning bolt type things are attracted to your fingers. That's a plasma. That's a plasma beam that's happening in there. It's very, very small amounts of plasma, but it is an example of plasma. A lot of times people say blood plasma. That's actually a completely different type of plasma. We're lucky that our blood plasma isn't so hot as to be the state of matter plasma. Blood plasma is a liquid. If we had plasma and we had that much of it in our bodies, we'd just completely burn up. So know that the plasma in your blood is a different type. The next thing I'm going to talk about is how we classify matter. And so take a moment to kind of look here in this chart. Basically, it breaks things down into mixtures and pure substances. The pure substances contain elements and compounds, and so you can sort of think of these as like only one chemical in there, all right? If it's a pure substance, like pure water is, H2O, all right? And that's a compound. It's got hydrogens and oxygens in there, but pure water would be H2O. Pure oxygen is oxygen gas, and that's all that's in there, all right? And so oxygen gas actually is O2, which is an element because it only has one type of atom in there, but we'll get to talking about that a little bit more in a minute. Mixtures, however, those have multiple chemicals in there, multiple different substances mixed together. And then they can either be mixed together heterogeneously, which means they're different throughout, or homogeneously, which means they're the same throughout. So talking about these different things, pure substances, when we say that they have the same composition, we mean all of the different parts are the same. So I give you an example here of sodium, and sodium is just, all of it is just sodium atoms, all right? Or if you had sodium chloride, which is salt, it would just all be NaCl, all right? And so all of it is the same all the way throughout. Mixtures, I should say, about that variable composition. I have pictured there something like a mixture of nuts and raisins and stuff like that in trail mix, or we've got that Kool-Aid man, emphasizing like when you make Kool-Aid, you mix different substances together. You have sugar in there, and you have water, and you have those little packets of flavoring, and those are all different chemicals mixed together. And then wood, we have starches, and we have all the things that go into cells. There's carbon and hydrogen and oxygen mostly all in there, but it's mixed together in these different ways. So even like the bark on the outside of the tree is different than the wood on the inside of the tree and things like that. And there are lots of different chemicals. Some trees have sap mixed in with them and things like that. And so mixtures are all sorts of different things. Pure substances are all the same thing. When we talk about the different properties here, pure substances, when we say they have the same set of properties, we mean if you have sodium chloride, if you have salt, all sodium chloride is going to act the same regardless. With a mixture, you have different things mixed together, and different parts of it might have different properties. And if you make the mixture slightly different, then the whole mixture might act a little bit differently and things like that. So you don't quite know with the mixture. A really, really big point with the pure substances, that those are elements or compound, is that they have a formula associated with them, and I'll talk more about that in just a second. Whereas you can't come up with a formula to represent mixtures. So for Kool-Aid, there's not like a KO on the periodic table to represent Kool-Aid. It's a mixture of other things, but there's no direct formula for Kool-Aid. All right, so now I'm going to jump in a little bit more depth. These are pure substances. All right, I'm going to talk about elements and compounds and how pure substances breaks down into these two different groups. The big thing with elements is there's only one type of atom in there. So that means there's only carbons or only hydrogens or only oxygens, just one thing there. All right. Compounds, on the other hand, contain multiple different types of atoms. We have up on the top right H2O, which is water. It's got hydrogens and oxygens in there. All right. So there are multiple elements, and in the formula, there's going to be multiple capital letters. All right. And if you can think of, like, carbon is just a capital C, whereas carbon dioxide is CO2, and that's a capital C, capital O2. And so carbon dioxide is a compound. It has carbons and oxygens in it, whereas carbon is just C. All right, it's just one thing. It's an element. Whether you're talking about elements or compounds, they all have unique properties. So water behaves in a very specific, very special way. That's a compound. Sodium metal behaves in a very specific, very recognizable way, and that's an element. And based on the ways that things react, we can kind of identify what they are. And so there are unique sets of properties here for these different pure substances. So now you can kind of go through and decide if some things are elements, compounds, or mixtures. I'm just going to bring the whole list up and talk about some of these. So here's this whole list. Stainless steel. So stainless steel is actually what we call an alloy, which is a mixture of metals. So stainless steel isn't just, there's no formula for stainless steel. It's the mixture of some different elements on the periodic table. And so and it's important to say that in a compound, things are chemically fused together. There's what we call a chemical bond between the atoms. In stainless steel, the things aren't bonded together. The metals are just mixed together. So any alloy is going to be a mixture, and stainless steel is one of those alloys. It has iron in it and carbon and some other things, zinc, I think, and but they're not chemically bonded. They're just mixed in with each other. Think of it like with stainless steel. Think of like melting down a bunch of metal and just stirring it together like in a pot. All right, so it stirs together, but it doesn't chemically bond, and so that makes it a mixture. Kool-Aid, very similar. So you put sugar in there, you put water in there, you put the little flavor packet, you mix it together, but there's not a chemical reaction that happens when you mix the Kool-Aid together, and so all those chemicals are still sugar and water and whatever the stuff is in the little packet, and a chemical reaction doesn't take place, and so Kool-Aid is a mixture of different things. Carbon is an element. It's on the periodic table. If you had the formula for carbon, it's just a capital C. Milk is a mixture of different things. It's got water in it. It's got milk fat. It's got lactose, which is a sugar in it. It's got calcium. There's a bunch of different things in milk. So that one's a mixture. Aluminum, that is on the periodic table as well. It's Al is capital A, lowercase l is the chemical symbol for it, and so that's just got one capital letter A. Co, that's cobalt. That's from the periodic table as well. It's an element. Cobalt only has one capital letter, that first C. O2 is called oxygen gas. It's a diatomic form of oxygen. So what happens is oxygen in its natural state exists diatomically, meaning that there are two atoms that are bonded together, but we consider O2 to be an element because all there is oxygen there. There's not another element together. So O2 having only one capital letter and having a formula, that makes that an element. Hydrogen is an element. It's on the periodic table. Iron is an element. It's on the periodic table. Nicotine has a formula. If you looked up the chemical formula for nicotine, you'd see what it is. It has carbons and oxygens and hydrogens and nitrogens in it. So nicotine has lots of different types of atoms in it, which makes it a compound. All right, it has a formula. It's a pretty big, complex molecule, but nicotine is a compound because it has a formula, and those things are all chemically bonded together. So that makes it a pure substance. Sterling silver is another alloy, so it's going to be a mixture of metals. NaCl is sodium chloride. That's got a formula there, so you know it's a pure substance. It's got two capital letters in there, the capital N and the capital C. So that means it's got different elements in it. It's got the sodium and it's got the chlorine. That makes it a compound. Tap water is a mixture of different things. It's got water in there, but it also has things like calcium from the pipes. Fluoride is added to tap water, things like that. So there's a bunch of different stuff in tap water. That makes it a mixture. Gasoline is a mixture as well. You know that there's like ethanol mixed in with gasoline, and there's E85, which is a type of gasoline with even more ethylene in it, and then or sorry, ethanol in it, and then you've got you know, different blends of gasoline. You've got the premium and the lower octane sorts of gasolines, and so gasoline is a mixture, and there are actually different mixtures of it. Sand is a mixture, different kinds of rock in there. CO, that's carbon monoxide, it's got two capital letters because it's got carbons in it and oxygens, all right, and so that is a compound. Soda is a mixture. It's got water in it and carbon dioxide and usually sugar and some other flavoring things, so soda is a mixture. MgCl2 formula there should clue you into the fact that it's a pure substance, all right, because it's got multiple capital letters there. It's a compound. It's got magnesium in it, that's the Mg, and chlorine in it, which is the Cl part. Okay, so magnesium chloride is a compound. It's got multiple elements in it. Tea is a mixture. It's got caffeine in there and the different things that give it flavor and aroma. And then it also, a lot of times people put sugar in their tea and things like that, so that would make it a mixture. A person, of course, is a mixture of a bunch of different things. We have a lot of different chemicals in our body, so water and fat and protein and all of these things mixing together inside of our body. Water there, when we say water, I'm guessing they mean like pure distilled water, and pure distilled water is a pure substance. It's H2O, which makes it a compound. Carbon dioxide, that's CO2, that has a formula, that's a compound. Sugar, in its most basic form, is glucose, that's C6H12O6. Has a formula, multiple capital letters, it's a compound. Air is a mixture of different substances. It's got oxygen gas in there, it's got nitrogen gas, there's carbon dioxide, there's argon, there's krypton, there's some other things. So air is a mixture. Crude oil, that's the stuff that comes out of the ground. That is a mixture of different things, different large carbon chains and things like that. And so we make that into different things like oil and gasoline and other lubricants, and we take different parts of the crude oil and we use it for different things. And so crude oil is a mixture. Lucky Charms is a mixture. You got different shapes, different some of the pieces are marshmallows, some of the pieces are not marshmallows, things like that. Bread, I would say, is a mixture. Not only does it have pockets of air in there, but there's a lot of different chemicals going into bread. You put flour in there and eggs and butter and whatever else. There's a bunch of different things in bread. Chocolate chip cookies is a mixture. You can clearly see that. Same thing. We got sugar in there, and we've got flour and chocolate and some other things. Pond water would be a mixture. There's water in there, but then there's also like the plant matter and dirt and mud and things like that. So pond water is going to be a mixture as well. So hopefully, I know that was a long list, but hopefully a lot of that made some sense to you. If you have any questions about any of those, you can come and ask me. So going on here, we're going to talk about two different types of mixtures. There's homogeneous and heterogeneous. Homogeneous, that prefix homo means the same. So homogeneous means the mixture is the same throughout, meaning that every time you took a sample of it, you'd get the same thing. I think of it kind of like taking an ice cream scoop and taking a scoop out of it. If every scoop is the same, it's homogeneous. If you might get some different scoops, then it's heterogeneous, meaning that there are different properties and parts of it. All right. So going through here, talking about homogeneous or heterogeneous mixtures. Stainless steel, again, it's an alloy, and most of the time, if you look at metals, if they're well made, they're the same all the way through the metal, okay? So this means that they're mixed well, they're melted down and mixed well. So alloys, I consider those to be homogeneous mixtures, meaning they're the same throughout. Kool-Aid, if you make it well, it's the same throughout. Milk is a special kind of compound called a colloid. Colloids have like sort of globs of things suspended inside of the mixture, and so milk, because there's little clumps of fat inside of milk, and you can't see them. They're even like microscopic little clumps of milk, but we consider milk to be heterogeneous because it's got these clumps that are much larger than individual atoms or molecules, and so it's kind of important that you know that stainless steel and all the alloys are homogeneous, but milk being a colloid and any other colloids, those are heterogeneous. Jello, like Kool-Aid, if you've made it well, should be the same throughout, so that's homogeneous. Sterling silver is an alloy, so that should be homogeneous. Tea, if you've made it well, hopefully, you know, all the different sips of your tea are the same. If you've made it like me, maybe it's got like tea leaves in the bottom, and it's got like maybe some extra sugar in the bottom because I didn't stir it well, then it would be heterogeneous. But if you make the tea well and get everything all stirred and you filter out the leaves, then tea would be homogeneous. Tap water should be the same as you drink it. You hope that it's the same throughout. Gasoline, hopefully, if you're going to be putting it in your cars, it's the same gasoline all the time running through. Otherwise, that might cause problems for your engine. Sand, if you pick up sand and you look at it in your hand, you'll see that different bits of it are different. Like there are parts of it that have one color and parts of it that have a different color, and you might have like a shell in there and different kinds of rocks. So sand is heterogeneous. Soda pop, similar to Kool-Aid and those things, you're drinking it, you'd expect it to be the same throughout. All right, so that would be homogeneous. A person is heterogeneous. Different parts of our body have different things. We've got our blood that flows in our veins. We've got our muscles that are made of different tissues and things like that. And so, like, people are definitely heterogeneous. We're not the same all the way through. Air. Air is an interesting one. If you get a really small scale, you would consider air to be homogeneous. But if you're talking about large scale things, like if you're talking about in a city or something like that, air would be very heterogeneous. Different places in the city might have different types of air. So that's something to think about. Bread, I would say, is heterogeneous. The crust of the bread is different than the inside, and also there's little air pockets inside of the bread, which I think makes it heterogeneous. Crude oil is also heterogeneous. It has like tars in it, and then it also has lighter stuff that floats on top and things like that. And so there are a bunch of different things in crude oil, and they're not evenly mixed together. So I'd call crude oil heterogeneous. Lucky Charms, different bits of it are different, so that's heterogeneous. Chocolate chip cookies, different bits are different, so that's heterogeneous. And then pond water, if you think about all the little things like floating on the top and the way that it looks, that's definitely heterogeneous as well. Those, again, I went through them pretty quickly. If you have any questions on any of those, please feel free to ask. All right, I'm going to move on to something else here. We're going to talk about different ways of separating things. So basically, if you have different substances and they're mixed together, we're talking about how to get them separate. So the first one we're going to talk about here is evaporation. You should have done this in your lab. What you do here is you have a solid and a liquid that are mixed together. This would be the case if you wanted to isolate the solid and get that by itself. You'd put it in a little dish, you'd evaporate the liquid, and the solid would remain. All right, and so you'd get to collect the solid. This isn't good if you wanted to collect the liquid because the liquid is boiling away and entering into the air and there's no way to get it back. So this is really just if you wanted the solid that was dissolved inside of the liquid. If you want to collect the liquid that boils away, distillation is a lot better process. You can see here with this one, there's a tube on top, and we've got an Erlenmeyer flask, and you would boil that Erlenmeyer flask, and then the vapor, rather than escaping into the outside atmosphere, it goes into this glass tube. Inside the glass tube, it's cooled. A lot of times there will actually be water running around the outside of this glass tube to help cool it down, and then you can see it's collected on the other side in what's called the distillate. All right, and that distillate is the stuff that comes out. And so this would allow us, if you say had salt water and you wanted to purify it into distilled water, pure water, what you could do is you could boil it and collect the water vapor and cool it down over on the other side, and then you get pure water without any salt in it. Another thing you can do here is you can separate two liquids that are mixed together as long as they have different boiling points. For instance, water and alcohol have different boiling points. Alcohol boils at a lower temperature than water does. And so what happens here is if you boil water and oil together, not water and oil, water and alcohol together, the alcohol is going to boil at a lower temperature, and then you can collect it in that tube and recondense it. And then as long as you keep low enough, the water won't boil and it will stay in the flask on the left-hand side there. All right, and so then you could separate two liquids based on their boiling point. And the more significant the difference in the boiling point is, the better this distillation process is for separating two liquids. Another method here is filtration. So what we do here is we use a piece of filter paper and a funnel. You dump the solution that you want to filter inside of the funnel. The liquid part drips through and the solid is collected in the filter. We did an example of this in lab as well. You'd usually use this for heterogeneous mixtures. If it was all homogeneous, if it was all the same, then everything would pass through the filter and nothing would be collected. And so filters work good for heterogeneous mixtures of liquids and solids so that you can get the solid out of there. And then we have this last one, which is called chromatography. The way this works is that different substances move through what we call a medium at different speeds. And so what we've got in this picture here is what's called chromatography paper. And what I think this is it's some different plant pigments that have been put inside the paper, and they move through it at different speeds. So like the carotene here moves through it the fastest. It's moved really quickly through there, and we get carotene collected on the top. The other stuff, the chlorophyll A and chlorophyll B, not moving through as fast. Okay, and so it's more towards the bottom. And what happens here is because carotene and chlorophyll have different sized particles, and so when they move through this, and what this is like a paper towel or something like that, and you get the water absorbing into the paper towel, and as it's absorbing and moving through there, the carotene moves faster than the chlorophyll, and so the carotene will get there at the very end and the chlorophyll's at the beginning. And so what this is we separate these substances based on how fast they move through this, what we call a medium, which is, a medium is just something that something moves through. So these are moving through the medium of this chromatography paper. And then what you could do is you could just simply snip it into bits. You could cut it between where each of these chemicals are, and then you would have them isolated from one another. Additionally, you can separate things here. It says based on any physical property. What I mean there is like if you had iron mixed in with some other things, well, iron is magnetic, so you could maybe use a magnet to separate iron from some other things. You could just physically use your hands to sort things apart from one another. Some things you can sort because some things will float and other things will sink. So if you dump them in water and you skim off the top, okay, you can take the particles that float and separate them from the particles that sink, and things like that. So these are all different methods for separating different chemicals that have been mixed together. The last thing I'm going to talk about here are chemical and physical properties. So a physical property is something that you can look at and you can observe it without changing the substance or without any chemical reaction happening. Chemical properties, when you observe a chemical property, you have to do something chemically to it to observe that property, and that means that a sort of small chemical reaction would occur. To give you some ideas of some examples here, color and mass and state. So color meaning like you look at something and you can see what color it is without ever interacting with it other than just looking at it. The mass, you can put something on a mass balance and figure out how much matter is inside of it without reacting in any way. The state of matter, whether it's a solid, liquid, or gas, you can observe that. Density can be measured. Melting point and boiling point are interesting. Melting point and boiling point, this means that if you heat it up to a certain temperature, it will melt. Well, when something melts, it doesn't change the chemical that it is. For instance, if we take ice and we melt it into liquid water, it's H2O both times. And so like we're not altering a substance by melting it or boiling it, and that means when you find the melting point or the boiling point, that's just a physical property, and that's the temperature at which it boils. That's what the melting point and boiling point are. Well, the melting point is the temperature at which something melts. Boiling point is the temperature at which it boils. And then volume, of course, yeah, you can directly measure volume without changing the substance or reacting the substance with something else. Reactivity, flammability, corrosiveness, flashpoint, toxicity. I'll talk about these a little bit. Reactivity, what you do with reactivity is you'll mix it with something and see if it reacts. So like you test to see if things are reactive with water. Sodium metal, for instance, if you put sodium metal with water, it just explodes, and so that's highly reactive. But if you put a lot of other things with water, they don't react at all, and so that's a reactivity test. Flammability is testing whether something catches on fire or not. You need to go through a chemical, reaction to see if that happens or not. So that's a chemical property. Corrosiveness says that if something will sort of tarnish if you put it under acid. Flash point is the temperature that you have to heat something to until it starts burning and like it combusts into flames on its own. And so flash point, you change something because a chemical reaction happens when something is burning. And toxicity is like poisoning, and the way that you have to test that is to see if there are chemicals in there and to see how those chemicals react with, say, things in your body. Also, taste and smell, I think, are interesting ones. Those ones are chemical properties as well. We have little sensors in our tongues and stuff like that that will react with stuff like acids. If we have something that's acidic in our food, we'll say that it tastes sour. And that's a little chemical reaction that happens there. So taste and smell are also included in chemical properties. Now I'm going to talk about physical changes and chemical changes. This is slightly different. A property is something you observe or measure. A change is when you see something changing, right? Okay, so like if we talk about a physical change, it's a physical change if it changes, but if it doesn't have a change in what the chemical is, so it's still the same composition. And so some examples here that I give, a change of state, that would be like melting or boiling. And I talked about this before. If something melts or boils, it stays the same substance, so it's not going to be a chemical change because it goes from just being liquid water to being gaseous water, for instance. It's still water, all right? When you boil something, it's still water. And so we say it's a physical change. Cutting something in half, so if you have wood and you cut, or a piece of paper or something like that, you cut it in half, it's still the same chemicals. If you paint over something, a chemical reaction isn't happening there, you just have one thing covering up another thing. If you break something in half, similarly, it's going to be the same substance. You haven't changed what the substance is there. And dissolving is a little bit more controversial. Some chemistry people would say that dissolving is a chemical change, but what it is it's just the particles kind of spreading themselves out in a liquid, so lots of people think that that's a physical change. Chemical changes happen when a chemical reaction occurs, and there are some different substances created here, and so that's the idea. Some different evidence that a chemical change has occurred. So if you mix two things together and they're kind of both room temperature, and then it gets really hot or really cold, that's a sign that a chemical reaction has happened and that a chemical change has occurred. If you see a chemical, like a color change, and we saw this in some of our labs, you dump two things together and originally, they're colorless and all of a sudden it's blue, all right? Or if you mix some things together and it was blue, but now all of a sudden it's green. If you get a color change that happens, a chemical reaction has probably occurred. If something didn't smell originally and all of a sudden there's a new odor, a chemical change has probably occurred. This precipitation, that's what's shown here on the picture to the right. What happens here is sometimes you can dump two colorless liquids together and a solid is formed, and so that's what we see there. There's a yellow solid. It's like a cloudy solid substance forming when you mix those two things together. If you see that phenomenon happen where you mix two liquids together and a solid is formed, that's called a precipitate, and that means that a chemical reaction has probably occurred. Also, if you're seeing a lot of bubbling or gas being created or fizzing, that is a sign that a chemical reaction has occurred. So all of those things kind of go to show that you've got a chemical change occurring within this. Alrighty, that is actually it for this presentation. I'm not going to worry about that last slide because it's not terribly important, and so these are the main things here. I know that there was a lot in this presentation, and so take some time to look over your notes, make sure you understand things fully, and as always, if you have any questions, come in and ask.